Okay, in our last case, we looked at the uniformly distributed load, and we showed how to graph these things quickly. Now let's look at a triangularly distributed load. I'm going to let you figure out the reactions. I'll give you the reactions, but I'm not going to solve for them. If I say that this is a maximum of, let's call this P. So what does this mean? This means that W of 0 equals 0, and W of L equals P. So okay, so, well, we have that. And if I have this load case, then it turns out that my total, or my reaction here is going to be PL over 6. My reaction here is going to be PL over 3. And if you add these two together, equals PL over 2, which is the area of this triangle, which is what you'd expect. Okay. As usual, let's draw the key points. Let's look at our shear diagram. We go up by PL over 6 here. We go down by PL over 3 here. I just have this, I'm trying to keep this to scale. So this is 1 point up, this is 2 points down. Because this one is twice the magnitude of this one. And they're pointed in opposite, not pointed opposite. You go up here, and remember when you're going from right to left, you do the opposite, so you go down here. Now remember that your shear is the integral of your distributed load. If you add up all the forces acting at any from here to a given point, you will get your shear at this point. So shear represents the accumulation of forces that are running through the plane, I guess, if you want to put it that way. So what does that mean? That means that dv of x dx equals omega of x. So what should this tell you? Here omega of x is 0. So that should tell you that you have a 0 slope here. And what happens over here? Your W of x is equal to P. Your slope should be most negative here. Yeah, most negative. Most negative. And most negative slope would be this way. And now you just want to connect these two. You know that it has, so we have a linear function here. This is technically a linear function, but the more accurate term would be to call it a constant function, because it does not change with x. And so it is a constant. Here we have a linear function, which does change with x. We do this. So this is, the equation for this is W. Let's write the equation for this. If we try to write an equation for W of x equals mx plus b, b is 0, like your omega starts off at 0. And what is your m? Your m is equal to negative p over l. Negative p over lx. So over here you have your maximum load p. So I should drop this sign here because your load is pointed downwards, but I already drew my arrows pointed this way, so I don't need to include this negative sign. Your omega of x You agree, right? Because if I have x equals 0, I have 0. Right? W of 0 equals 0. P times 0 over L equals 0. If I'm at point L, I should have my maximum load. When x equals L, I have P. And both those things check. Okay, and then for this, we just need to connect the dots, really. I already drew in the slopes here, and because I drew in the slopes, I know that I can just, if I don't force it, if I just let it naturally, then this we know that this line has to coincide with the center of this force. The reactions are due to the center of the reactions are due to the distribution of your load here. So you can actually ignore the reactions when you're trying to find out where the center of this thing is. Once you find the center of this, that is where, because you know the center, it's balanced on either side. I mean, if it's balanced on either side, then it's not likely to tip. You don't have a force that's greater on one side than you do the other. So that's why it's 0 here. You have 0 shear, you have 0 forces introducing instability. Now the interesting question is what happens to your moment? And before I forget, notice how this equation, the highest power here is x to the 1. Here, I'm not going to write out the equation for this, but it's going to have some constant x squared. Constant times x squared. We're going up in power, right? We went from 1, we're going to 2, and now we had 1 because we have a triangular load. Here we had a constant load, so our x was to the power of 0, right? Because x to the power of 0 is 1. Here we have this. So our m of x, that should tell us that our m of x is going to be proportional to x cubed. Now, let's look and see what happens. The slope here, or the slope of your moment diagram is your shear diagram, and moment is positive here, negative here. So if this is positive, that means I should have a positive slope here. This is very negative though. This is more negative than this is positive. As a matter of fact, it's more negative by a factor of 2. So let's make this extremely steep here. And then if I carry this down, remember that wherever your shear is 0, you should have a maximum or a minimum in your moment diagram. And if I do this, yes. Notice that your graphs are, let me zoom out a little. Your graphs are all, they appear shifted. That's because your center is not at x equals L over 2. Your center is at x equals 2/3 L. X equals 2/3 L. So this is shifted away from the center. This is shifted away from the center, but it's perfectly fine. Okay, so we've done. Yeah, I'll leave it at that for now. Yes, if you want to calculate you can get these equations just through integration. Once you find out what your shear should be, and you can just integrate your shear. You'll have a constant in your shear term. Sometimes you'll have an applied moment. That's where that constant comes in. But yeah, let me start the next one. I'll do a more complicated. I'll try to do a more complicated example in the next video.